In this video, we will learn how to calculate probabilities. And so we're going to start off with the classical probability formula. This only applies when there are equally likely outcomes, which I'll explain. So for an experiment with a sample space S of equally likely outcomes, the probability or the chance of an event E occurring is given by P of E is equal to, and here we have, this notation represents the number of elements in E, and then we divide by the number of elements in S. So let's do a quick example. So let's suppose I have an experiment. In the experiment is that I roll an octahedral die. So that's an 8-sided die, meaning that the numbers 1 through 8 are on the 8 faces of the die. The first question is, what is the sample space? So recall that the sample space is the set of all possible outcomes. So if I roll the 8-sided die, the sample space S is just 1, 2, 3, 4, 5, 6, 7, and 8. So that means this number here is just going to be 8, right? So let's move to the next question. The next question is, what is the probability that the upward number, the upward face is not 1, 3, or 5? So what is the probability? So remember, we've got our formula up here. The probability that it's not 1, 3, or 5 is going to be the number of elements in whatever this event is divided by the number of elements in the sample space. So I'm going to say that the probability of not 1, 3, or 5 is, so this is going to be the number of things in our event, and I'm just going to call this event E. Okay, and the number of things in the sample space. So we already said there were 8 things in the sample space. And how many things are there in this event? Not 1, 3, or 5. So that would be 2, 4, 6, 7, or 8. So there are 1, 2, 3, 4, 5 things. And that is our final answer, 5/8. And written as a decimal, this is 0.625, which is 62.5%. Okay, let's move on to the next question. What is the probability the number on the upward face is a multiple of 3? Okay, so let's see. This is probability multiple of 3. So let's just call this event E. So that's going to be the number of things in the event E, and we know there are 8 things in the sample space. So in this case, well, how many of these things are multiples of 3? I only see 2 things, so this will be 2/8, which is just 0.25 or 25%. So that's our probability. Okay, so in this example, 2 regular 6-sided dice are tossed. What is the sample space? Okay, and if you recall, there were 36 things in the sample space. So these are all the different things that we can get. We can roll 2 1s, a 1 and a 2, etc. And another way that you can write out the sample space is you could just list the number of dots or pips that are on the upward face of the die. So we could have like 1, 1, 1, 2, 1, 3, etc., all the way to 6, 6 over here. So that would be our sample space. And remember, the number of things in the sample space, by the way, is 36. So let's answer the next question. Compute the probability that the sum of the pips or the dots is 7. When would the sum be 7? The sum would be 7 when, so here are some possibilities: when one die has a 6 and the other has a 1, or if we first die and the second die, the opposite happens. We also have if there's a 3 and a 4, or a 4 and a 3, a 5 and a 2, or a 2 and a 5. So I'm just like listing the different ways you can get 7 from dice. Okay, and if you want to think about this visually in our diagram, these outcomes correspond to these 6 things right here. Those all add up to 7. The probability that the sum is 7, and let's call this our event E, is equal to the number of outcomes in E divided by the number of things in the sample space. So we know that that's 36 things in the sample space, and we have 6 things in this event E. So 1/6 is our final answer. So let's do another quick variation of this question. What is the probability for C? Compute the probability that the sum of the dots is 13. So if you think about that for a minute, the largest number we can get as a sum is 12. So the probability of getting a sum of 13 is 0. Okay, let's do another example, part D. Compute the probability that the sum is at least 11. So let's think about, that means 11 or more. So in this case, that just means 11 or 12. So if we think about it, we know that 11 or 12, we have, if we roll 6 in a 6, that would give us 12. That's the only way. In order to get 11, we would have to roll a 5 in a 6 or a 6 and then a 5. So there's 3 ways. So the probability of getting some at least 11 is equal to, it looks like we have 3 possibilities here. So 3 over 36, and that is just 1 over 12, and that would be our final answer. Okay, let's do another example. In part E, compute the probability that the sum of the dots is at most 4. So at most 4, in this case, well, we can't roll 1. The smallest is 2. So 2 or 3 or 4. So this will happen if we get a 1 and a 1, 1, 2, or 2, 1. And then we have 3, 1, or 1, 3. And you can also roll a 2 and a 2. And I believe that's all. Those are the only ways we could get 4. So there are 1, 2, 3, 4, 5, 6. So again, probability sum is at most 4 is equal to the probability sum is 2, 3, or 4, which we counted as 1, 2, 3, 4, 5, 6. 6 out of 36 things in the sample space. So again, we have 1/6. And here you can see I've circled all of the outcomes where the sum is at most 4. And you can see there's 6 of them. So let's do another type of example. This time we're going to deal with cards. So a card is selected at random from a standard deck of playing cards. A is compute the probability the card that's drawn is an 8. So I just want to bring your attention and remind you the standard deck of playing cards has 52 cards and they are in 4 suits. So we have, and then we have 4 kings, and we have 4 queens, and we have 4 jacks, and here are 4 suits. So the probability the card is that we draw an 8, and let's just call this event E. This is just the number of ways, the number of outcomes in E divided by this number of things in the sample space. And we know that there are 52 cards. And the number of things in E, well, there's the 8 of diamonds, 8 of hearts, 8 of spades, and 8 of clubs. So that's just 4. And you can reduce that down to 1/13. Okay, let's move to part B. Compute the probability the card is a king or a queen. So probability king or queen. And let's call this E. So we already looked at the deck of cards. So we know that there are 52 cards and there are 4 kings and 4 queens. So there's 8 cards that could be drawn that would satisfy this. So 2/13 is our probability. So here's another example from our text. This involves the Punnett squares. So in a certain species of animal, the gene for black fur is dominant, while the gene for white fur is recessive. If two animals with genotype capital B lowercase b are bred, what is the probability that their offspring will have black fur? Okay, so in this example, I'm going to start off by setting up the Punnett square. And so I'm going to write down the genotype for one parent at the top. So there's this parent's genotype is one dominant and one recessive. And I'm going to write down the genotype for the other parent over here. So we have one dominant and one recessive because both parents have this. So here are the possibilities. We could have BB, capital B, capital B. We could have mixed. So I'm just looking at these guys, or we could have two recessives. And so since capital B, the black fur is dominant, in this case, we're going to have black fur. In this case, we're going to have black fur. In this case, we're going to have black fur. But when we have two recessives like this, we'll have white fur. And these are all equally likely. So we can use the probability formula, and we say the probability of getting black fur for the offspring to inherit and have black fur would be the number of things in let's call this event E. Number of things in event E divided by the number of things in the sample space. There are 4 things in the sample space. So we have a 4 here. And how many of these cases will the animal have black fur? 3. So this is going to be 0.75 or 75%. So we're going to move on to the empirical probability formula. And this formula is more based on just observations. So it's not so theoretical. It's more just based on what did you observe in your experiment or what did you observe in the population. So in this case, the empirical probability of an event is just given by the number of times the event occurs over the total number of occurrences. So here's an example. 381 voters were surveyed, and the results are summarized in the table. So you can see the voters were asked if they identified as male or female. They were asked if they were identified as Democrat, Republican, Independent, or other. And then the bottom row and the right column are just totals. So let's look at the first example. Compute the probability a randomly chosen voter is a Democrat. So the probability of Democrat, we would just have to look at, well, how many Democrats were there? There were 160 Democrats, right? We don't really care if they were identified as male or female. There were 160, and then we're going to divide that by the total. So I'm just using the formula here. The number of times E occurred, so the number of times someone surveyed said they were a Democrat, and the total number of times occurrences corresponds to the total number of people surveyed. And so this gives me 0.4199, which if I look at this as a percentage, it's 41.99%. And if I round that to 1 decimal place, I have, so basically we're going to have 42.0%. So in this case, independents are here, females are here. So female and independent, we just have 22. So the probability female and independent would be 22 occurrences over the total, again, is 381. That gives me 0.05774, which is 5.774%. And if I round this to 1 decimal place, I will get 5.774%. 0.8%. The very last thing I want to mention is this idea of odds. So what do we mean when we say the odds against or the odds in favor? So let E be an event, and we're going to go back to a sample space that has equally likely outcomes. So let F be the number of outcomes in favor of E, and let U be the number of outcomes unfavorable to E. Okay, so then we say that the odds in favor of E are given by F to U. So you can also write this as F dot dot U, and you can calculate it as a number as F divided by U. And then we have the odds against E are given as, we would say U to F. So we just put the number of occurrences unfavorable to E first. That's the only thing that really happened. We just flipped these two things. And we could write this as U dot dot F, and it calculated as a number. This would be U divided by F. So let's do a quick example down here. A coin is tossed 7 times. What are the odds in favor of getting 7 heads? Okay, so we have to calculate the odds in favor. What we really need to do is we need to figure out what F is and what U is. So remember, F is the number of outcomes favorable to E. Well, let's look at the total number of outcomes. So the total number of outcomes, if I flip a coin 7 times, remember the counting principle? So this is like we have 7 trials. Each toss is a stage, right? And we just keep tossing 1, 2, 3, 4, 5, 6, 7. And for each toss, like the first toss, there's 2 possible outcomes. For the second toss, 2 possible outcomes, etc. And so this is just 2 to the 7th, which is 128. So those are the total number of things in the sample space. There's 128 possible outcomes. How many of those outcomes are favorable to getting 7 heads? Well, there's just one, right? It's just heads, 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 heads. That's it. So the number of things that are favorable are just 1. And then everything else here, we have 128 minus 1. So the unfavorable would be everything else, and that's 127. So the question asks us odds in favor. That's always putting the F first, the favorable first or on top. So the odds in favor, let's finish this off, will be, we can write this as 1 to 127, or we can write this as 1 colon 127, or we can write this as 1 over 127. So these are 3 different ways we can write the odds in favor of getting 7 heads when we toss a coin 7 times.